And let's show next that outer measure is translation invariant. That is, for any set A and any real number y, the outer measure of A plus y equals the outer measure of A. By A plus y, we mean take every element of set A and add y to it. It's a rigid translation in that sense. And the proof is based on the translation invariance of bounded intervals, bounded open intervals. Okay, so claim is outer measure of A plus y equals the outer measure of A. First, let's consider the case where A has finite measure. Say that measure is capital M. Then for all epsilon greater than 0, we can find a specific collection of bounded open intervals, I sub n, that covers set A, and the sums of the lengths of those I sub n's is less than m plus epsilon. This is why we did that theorem 0.3 stuff where we related greatest lower bounds and least upper bounds to epsilon quantities, because it comes up right here. Now, the idea is the m value, the outer measure of A, is an nth of all such type sums. So if this is an nth and we add a little bit to it, we can find a specific element of the set, a specific collection of open intervals, the sums of whose lengths is less than m plus epsilon. The fact that m is an nth, you add a little bit to it, something bigger than the infimum of the set, I can find specific elements of this set. This was that set x sub A and x sub B that we dealt with in the lemma where we were showing monotonicity. So important idea, we use these epsilon arguments quite often, follows from properties of infima of sets. So take a real number y, we'll use this for the translation. If the I sub n's cover set A, then the I sub n plus y's, n equals 1 to infinity, is understood. If we take this collection of open intervals, bounded open intervals, they cover set A plus y. If the I sub n's cover A, the I sub n's plus y covers A plus y. So the outer measure of A plus y, that's the nth of the sum of the lengths of all coverings of set A with the appropriate properties. Well, this is one of them. The I sub n plus y's are a covering of A plus y by bounded open intervals. So if we sum up the lengths of those, remember outer measures are nths, and the nth is less than or equal to this specific value here. And here's where we're using the translation invariance. Well, the length of I sub n plus y is the same as the length of I sub n. If I take an interval and translate it, its length doesn't change. For example, if we look at interval I sub 1 here, say it has endpoints A sub 1, B sub 1, notation we used previously. The length is B sub 1 minus A sub 1, right-hand endpoint minus left-hand endpoint. Well, what if you translated that interval by y? Well, then I'd add y to the left-hand endpoint, I'd add y to the right-hand endpoint, and when I took right-hand endpoint minus left-hand endpoint, the plus y's would cancel out, I'd get B1 minus A1 again. Yeah, length is translation invariant, simply based on the way that it's computed. So we can replace the lengths of the I sub n plus y's with the lengths of the I sub n's, and we get something less than m plus epsilon because these I sub n's were chosen in a way to be less than m plus epsilon. We have now shown that the outer measure of A plus y is less than m plus epsilon, where epsilon is an arbitrary positive number. Well, then we can make epsilon as small as we want, and we can get m as an upper bound on the outer measure of A plus y. We do pick up an or equals to standard analysis argument. The outer measure of A plus y is less than or equal to m. Okay, we want to show it equals m, the outer measure of A, so we're halfway there. All right, now what we're going to do is similar to what we just did, but we're going to take, let's denote it with j's, because it's not exactly the same. Let j sub n be a collection of bounded open intervals such that the union of those bounded open intervals covers A plus y. So now we're covering A plus Y, and we're going to relate those to a covering of set A. Easy enough, we'll just subtract Y. Assume the sum of the lengths of the J sub n's is less than n. We're going for a contradiction. Little habit of mine is when making a little argument by contradiction, I'll write in capital letters the assumption where the argument starts, and in capital letters the contradiction where the argument ends, just to see these little sub-arguments within these proofs. Some of these proofs are very lengthy. Not so much these we're doing just yet, but let's assume the sum of the lengths of the J sub n's is less than n. Well, now the J sub n's cover A plus Y, so if we take the J sub n's minus Y, they'll cover A plus Y minus Y. That is, they'll cover A itself. So we've taken, in the first argument, we've taken the I sub n's that cover A, added Y to them, and covered A plus Y. Here we're taking J sub n's and covering A plus Y, subtracting Y from them to get a covering of A itself. So similar to the first argument, we're just covering the other set. So the J sub n minus Y's, they are a covering of set A. If we sum up the lengths of the J sub n minus Y's, that's the same as summing up the lengths of the J sub n's. It's just used and just argued. Length of an interval is a translation invariant thing, and we've assumed the sums of these lengths is less than n. But wait a second, that means we've covered set A with a bunch of open bounded intervals, the J sub n minus Y's, the sums of whose lengths is less than m. You can't do that. You can't cover A with a bunch of open bounded intervals, the sums of whose lengths is less than m, because the outer measure of A equals m. That's the nth. You can't get something smaller than the nth out in this process. That's what the contradiction is. So the contradiction shows us that our assumption, sum of the lengths of the J sub n's is less than m, that must be false. The sum of the lengths of the J sub n must be not less than m. That is, must be greater than or equal to m. So what we've done is we've taken J sub n, an arbitrary collection of bounded open intervals that covers A plus Y, and we've shown that the sum of the lengths must be greater than or equal to m. Arbitrary collection of such J sub n's. So if we took the nth of this sum over all collections J sub n, we would get something that's greater than or equal to m. In other words, the outer measure of A plus Y is greater than or equal to m. Combined with this up here, we've got the outer measure of A plus Y and the outer measure of A, they're equal. For set A having finite outer measure. May I mention in passing, don't construe finite measure as meaning bounded in some sense. We've used a lot of bounded stuff as of late. It was always intervals though. When I say the outer measure of A is finite, I'm not saying A itself is a bounded set by any means. Remember, the rational numbers, they got measure 0. That's not a bounded set though. There's rational numbers everywhere, almost everywhere in some sense. But don't confuse this with boundedness. The measure's bounded, but set A itself may not be bounded. Okay, but we still have the case when the outer measure of A is infinite. So next, suppose the outer measure of A is infinite. Then if we take any collection of, and this infinity is an infimum, so when we take any collection of I sub n's of the appropriate type that covers set A, when you add up their lengths, it must add to infinity. We're dealing with all these lengths. These are non-negative quantities. When we sum them up, when they converge, we have absolute convergence. So we can maybe move the sums around, a little result from calculus 2, I think. But it makes sense for the series of these non-negative numbers to diverge to infinity. They must. If any of them were finite, we took an nth, it couldn't be itself infinity. So sums of the lengths on any such covering must be infinite. Consider A plus Y. Take a collection J sub n of bounded open intervals such that their union covers A plus Y. Subtract Y from them, as we did above. This is a bounded set of open intervals, the J sub n minus Y's, that covers set A, as before. So the sum of the lengths of the J sub n minus Y's has to be infinity. If you ever cover set A with open bounded intervals, the lengths have to sum to infinity. This is a covering of set A with bounded open intervals. Okay, then the sum of the lengths must be infinity. Oh yeah, but the length of J sub n and the length of J sub n minus Y, as before, are the same. Length is translation invariant. So I can replace the length of J sub n minus Y with the length of J sub n for each of those, and we get the sum of the lengths of the J sub n's must be infinite. We took an arbitrary set of bounded open intervals that covered A plus Y, and we saw the sums of the lengths are infinite. So taking an inf over all such values produces an outer measure for set A plus Y of infinity as well. Cover it with any collection of open intervals, the sums of the lengths must be infinite. So it, A plus Y, must have outer measure infinity, which was the hypothesized outer measure of A. So the outer measure of A plus Y equals the outer measure of A, taking care of infinite outer measure in a separate case. So that was all possible situations here. And we see that outer measure is translation invariant. The outer measure of set A equals the outer measure of set A plus Y, where Y is any real number and A is any subset of the reals. All right, property 3 in our wish list of properties for a measure was countable additivity. We're not showing countable additivity. We're not saying countable additivity doesn't hold for outer measure. It doesn't, but we ain't saying that yet. It'll take us a while to get there. But this is a result related to countable additivity called countable subadditivity. And I think we've encountered this before in the previous section. Outer measure is countably subadditive. That is, if we take a countable collection of sets, then the outer measure of the union is less than or equal to the sum of the outer measures. You might intuitively think, and your intuition's probably going to be in pretty good shape when it comes to Lebesgue measure, maybe not for outer measure though. You might think, well, yeah, you didn't say anything about these E sub k's being disjoint. So maybe they overlap, and that's why when you have the sum on the right, you get something bigger because you've counted pieces that overlap more than once. Maybe. I ain't ready for this, but yeah, they could be disjoint and we could even get a strict inequality here. That's a problem. A problem we're going to have to resolve somehow or other. And the resolution will lead to Lebesgue measure. But outer measure does have this countable subadditivity property. It doesn't, outer measure doesn't have countable additivity. We got to have countable additivity. So we'll have to fix that. But let's go through a proof of this one. Subadditivity. Hey, if the outer measure of any of the E sub k's is infinite, this right-hand side's infinity and the result holds trivially. So without loss of generality, we can assume finite measures on all of the E sub k's. All right, then it's just a little epsilon type argument. For all epsilon greater than 0, and for every k, so we're doing an epsilon argument on the E sub k's, all of them. There's a countable set of open intervals. Let's denote them as I sub k comma I, where I ranges from 1 to infinity, such that E sub k is a subset of the union of those things. All right, so for E sub 1, we've covered it by intervals I sub 1 comma I, for I equals 1 to infinity. For E sub 2, we've covered it with the intervals I sub 2 comma I, for I equals 1 to infinity. Know what I mean? So we've got a countable collection of open bounded intervals that covers E1. We got a countable collection of open bounded intervals that covers E2, and so forth. So we've done this for all natural numbers k. So we've covered every E sub k with a countable collection of bounded open intervals. Oh, and we can make the sums of the lengths of those intervals less than the outer measure of e sub k, the infimum, plus epsilon over 2 to the k, plus a little bit. There's my wiggle room. I choose a wiggle room of epsilon over 2 to the k for some reasons to become apparent shortly. I know the outer measure of e sub k is an nth of such things as this. So if I go a little bit bigger than that, I start finding things such as this, elements of set x sub a in the notation we did in that first lemma. That property of nths versus epsilons again. So we've done this, think of k as fixed throughout this line. We fixed k and we have this kind of argument for k equals 1 and for k equals 2 and so forth. Well, now if we'll take that collection of open intervals, I sub k comma I, for all I a natural number and all k a natural number at the same time, we've got a countable collection of countable sets. Well, a countable collection of countable sets is countable. Theorem 0.10 in the background material. If I take all of those open intervals, the ones that covered E1 and the ones that covered E2 and the ones that covered E3 and so forth, all those open intervals together produces a countable set. And the resulting countable collection of intervals will cover the union of the E sub k's. The I sub 1 i's cover E sub 1, the I sub 2 i's cover E sub 2, and so forth. So all of these double subscripted i's cover all of the E sub k's, covers the union of the E sub k's. All right, so then we wanted to do that because we want to talk about the outer measure of the union. So the outer measure of the union being an nth of the sums of the lengths of all bounded open intervals covering the union of the E sub k's this time. So the outer measure is less than or equal to the sum of these lengths of this specific covering of the union of E sub k. Let's rewrite that a little more explicitly as a sum from 1 to infinity of a sum from I equals 1 to infinity, k equals 1 to infinity, and I equals 1 to infinity. This is more book notation. I think I probably inserted this to make it a little cleaner. So we've got a double sum. As I commented, we've got absolute convergence if we've got convergence at all. So I can rearrange these things as I see fit. We have absolute convergence. Be careful with rearranging series. We don't have a problem here. There's absolute convergence. Everything is non-negative. This is less than the sum from k equals 1 to infinity of these little things up here. We had, for a given k, we had the sum from I equals 1 to infinity of the lengths less than this quantity in terms of k. So for a given k, this thing here, the second sum is exactly this. Okay, so the second sum can be replaced with this and an inequality. And that's all we've done there is replace the second sum, the rightmost sum, with this quantity by the bound above and pick up an absolute value. Now, that took care of the first sum. Now we're summing from 1 to infinity on k. Well, that just give us a sum from 1 to infinity, outer measures of the E sub k. Excellent. By the way, that's the right-hand side of this equation. And to that gets added the sum from k equals 1 to infinity of these things here. Oh, you've got powers of a half. You've got a geometric series with ratio a half. That's why, in hindsight, that's why we chose this as the bound. So when I sum from 1 to infinity up, epsilon over 2 to the k, it sums up just to epsilon. So sums to just epsilon. I love them geometric series. Allows me to take an infinite number of things and get something finite out. I even know what the sum is for geometric series. So the punchline here is the outer measure of the union of E sub k is, the weakest part is here, is strictly less than the sum of the outer measures plus epsilon. Same idea. Epsilon can be made arbitrarily small and positive. In so doing, we draw the conclusion that the left-hand side is less than or equal to the right-hand side with the epsilon replaced with a 0. There's a limit basically being taken, and that's where the or equals to part comes from. And that's exactly what was claimed. The outer measure of the union is less than or equal to the sum of the outer measures. First off, yeah, that's not terribly surprising. What is terribly surprising is I can throw in the word disjoint, the hypothesis disjoint, and I maybe still can't get rid of the inequality. Worse than that, I may even get a strict inequality, as we'll see by example. So here's where we stand in terms of outer measure. We know for an interval, the outer measure is the length. The first thing we showed. We know outer measure is translation invariant. Proposition 2.2, the second thing we showed. We know outer measure is, it's subadditive, as just shown. And we know outer measure, by its very definition, is defined on the power set of the reals. Except for the sub part, that was the 4 desired properties of a measure, except for the subadditive. We wanted just countably additive, not subadditive. Well, it ain't like later on we're going to actually show countably additive. It's not. We're going to show it's not, in fact. So outer measure is awfully close. And that little highlighted part there, that's the problem with outer measure. All right. We've got to have countable additivity to do integration. We're going to set up sums like Lebesgue sums in a sense, and we're going to take limits in a sense of those sums, limits of sums or series. We're going to do it with soups and ants, but they're effectively limits. And we've got to have countable additivity. Subadditivity won't do to set up a theory of integration. So what we're going to do in the next section, section 2.3, is we'll introduce a condition. It's called the Carathéodory splitting condition. It's a very artificial looking thing that comes out of nowhere, but I'll try to verbally make some sense out of what would motivate them to look at this condition. Remember, the strategy is we're looking for countable additivity. So I'll try to motivate it with that as the thought. So we'll put a condition on sets, and sets that satisfy that condition are the kinds of sets we'll restrict our attention to. So we'll consider the collection of all sets that satisfy this Carathéodory splitting condition. And we'll consider outer measure on that collection of sets, not the power set of the reals, not every set of real numbers, the set of real numbers that satisfies this Carathéodory splitting condition. And that's what Lebesgue measure will be. It'll be outer measure restricted to this sub-collection of sets. So there's sets that aren't in this sub-collection. Yeah, there's a lot of them, in fact, in the cardinality sense. These sets not in this collection will be called non-measurable sets, and they'll violate countable additivity. We can even get them to violate finite additivity. So that's bad. That's very, very bad. Next is an exercise from the book. I won't go ahead and do this one. You probably showed this in senior level analysis. The interval 0, 1 is uncountable, is not countable. The argument in senior level analysis is the Cantor diagonalization argument. Standard argument, good argument, thing you ought to see in senior level analysis. We've got the equipment to give a rather short proof of this. It's because we know a little bit about cardinality and measure. 0 to 1, that's a closed interval. It's an interval, so its measure is its length. Proposition 2.1 says the measure of this interval is the length of this interval. Open, closed, I guess it doesn't matter. The length is 1. Now, we stated in some of the supplemental stuff, it was the Riemann-Lebesgue theorem supplement, corollary 6.9 in that if a set is countable, then it has outer measure 0. What we had defined was measure 0 at the time, but it's exactly the same as what outer measure 0 would mean in the current notes. So we can borrow that result. Countable sets have measure 0. So the contrapositive of that is if a set has positive measure, then it's not countable. So if countable, then measure 0. If not countable, so I get the logic straight here. If not measure 0, the only alternative is positive measure. There's no such thing as negative measure. If positive measure, then not countable. Negate measure 0, conclusion, and negate the hypothesis, countable. And lay the logic out in this order. It's a contrapositive of corollary 6-9. Well, this thing's got positive measure. It's got measure 1. Okay, so it's uncountable. So it's easy to establish the uncountability of any interval. Remember, intervals have distinct endpoints, and so they have positive length. So all intervals are uncountable. And there's a measure theoretic argument, kind of just for fun, since it's so easy. And it wasn't that easy when you did it in senior level analysis. Yeah, in senior level analysis, you didn't know stuff about measure, nor should you. One of the exercises also in this section gives some motivation for a further study of G-delta sets, how the G-delta sets pop up. G-delta sets, what was that again? Delta was intersection, G was open. A G-delta set is a countable intersection of open sets, recall. Exercise 2.7 says, for any bounded set E, there's a G-delta set, G, for which G covers E, E is a subset of G, and the outer measure of G equals the outer measure of E. Set G is called the measurable cover of set E. We'll see some more of this later. I'm not saying the sets are equal. I'm saying the measures of the sets are equal. And what was a G-delta set, one more time? Was a countable intersection of open sets. We set this measure stuff up by covering sets with bounded open intervals. Well, a union of a bunch of bounded open intervals is an open set. I guess we could put together some kind of epsilon argument and an intersection of those particular open sets that we would cover set E with in the definition of its outer measure. That's how the proof of this one works. So a little hint on this one, it's an excellent homework exercise, is to use an epsilon argument and a bunch of open sets and intersect them. Yeah, they use a bunch of open sets and intersect them. That's a no-brainer because that's what a G-delta set is, so that's got to be somewhere in there. But we're covering a set E, not with an open set here, but with a G-delta set, which may not be open, which has the same measure as, same outer measure as set E. I'd like to tell you what a measurable set looks like. Well, this looks like we're awfully close. G-delta sets, I don't know, measurable sets, well, this set E seems to look a lot like a G-delta set. It's got the same measure as a G-delta set. There's maybe some stuff in the G-delta set that's not in set E. How much stuff is that? Yeah, that becomes quite involved. And we'll explore this some more in the future. But there's a little motivation for G-delta sets. And that takes care of our definition of Lebesgue outer measure and some of the properties of Lebesgue outer measure. And the sticking out like a sore thumb thing that's missing is we never showed outer measure is countably additive. We only showed it's countably subadditive. But we got this close to our wish list of 4 things. But we didn't get there and we ain't gonna get there. So what we'll do in section 2.3 is try to deal with this insatiable desire for countable additivity. We got to have countable additivity to do what we're going to do. All right, that's going to mean going back to our wish list of 4 things and modifying one of them. We'll modify the last one. When we define Lebesgue measure versus Lebesgue outer measure, something different, Lebesgue measure, it won't be defined on the power set of the reals, but it'll be countably additive. So small price to pay. We've got to have countable additivity. So I will see you soon in section 2.3. We'll look at that Carathéodory splitting condition, see why it's relevant and what its implications are. Have a nice day.